Yeah.
I wanted to ask
Unless you embed those links, I don't think they're...
How do you embed them?
Good morning, everyone. Welcome to the last bucket course class before the holidays. I'm Joanne Bundy, and when you see me, you're supposed to remember, just please silence your cell phones and turn on your tea coil. I have an addition to the announcement that I made last week about Clark Lindgren being the first course starting January 11th after the holidays. And I know most of you, that's all you need to know is that Clark is going to be doing the course and you will be here. But I actually have the name of the course for you now. It's From Synapse to Self, how our synapses make and break us. I wrote this down because I wasn't sure how my synapses would do. So we will send out an email to all of you when it comes time to register, which will be about 2 weeks prior to the start of the class. And there is not going to be a sign-up sheet at Mayflower or at the library anymore. So you need to register from our website. Now, if you don't have a computer, find a friend who can register for you. And if push comes to shove, please call me. I'll make sure that you get registered, because we want to have you here. But it's turned out to be a very efficient way of getting our registration in and correct. And I can tell you that we close off the registration at 100. And with Clark's class, it will fill up in a hurry. So don't dally. I will be happy to have you. That's January 11th. This morning, we have a first-timer. You'll recall that the Fortnightly group has been good enough to share their lectures with us. And Fortnightly, for those of you who don't know, is a group of gentlemen from the college and from the community who get together every fortnight and exchange lectures. They take turns giving lectures to each other. And we wanted to get in on that, so we invited them to come and do open Wednesday classes for us, and they have been very accommodating to do that. Today we have Howard Raffety, who is an agricultural engineer graduate from Iowa State. If you've lived in town for more than a day and a half, you know who Howard and Susie are. They've been very successful farmers, and a few years ago they moved into town to Mayflower, actually right next door to me. And better neighbors you cannot find. So we're happy to have Howard here this morning, and he is going to be talking about oops, engineering goofs. And I found out something about myself. I can't say oops without raising my eyebrows. Are you that way too? If it just doesn't come out right. So we'll see how Howard does with that. So I'm delighted to present to you Howard Raffety. Oops. Howard.
Well, at least I didn't trip over the steps. Oops. How does this work, Bob?
Over the right ear, behind your head.
Horizontal behind your head.
Like that. Well, if it falls off, you're out of it. First of all, we've got to turn it on. Get the fingernail right here.
Whoops.
Come on. Come on.
To turn the ring.
Can't get the fingernail on it right. Ah, there we go. There we go. Now you got me. So, first thing, Joanne, can I get your phone number to put in my little black book since I don't do interviews?
Call me.
You wouldn't be as much fun. And secondly, folks, I'll give you warning. Bob and John tell me that today is free, and if it's free, you know what you get.
We get our money's worth.
That's correct. You got it. So, bucket course, November 2016. Got a light up here? As announced, I am Howard Raffety, and I have been around these parts for almost 76 years, come January of 2017. My family goes back to great-grandpa Elon, Civil War days. Sam was his son, Laverne, my dad, was Sam's son. All of Dad's generation, his siblings, Stanley Raffety, Lois Raffety Greenwald, Dad, Ruth Raffety, all graduated from Grinnell College. Dad was a successful teacher, coach, and administrator in Brooklyn from 1922 to 1930, before beginning a career as a farmer in 1930. My older brothers and sisters, sister, Maynard, Seymour, Carolyn, all attended Grinnell College. Seymour, Carolyn, and cousins Stan and Ruth Greenwald are Grinnell graduates. I said, enough is enough, and went off to Iowa State College, which became Iowa State University while I was in attendance. The disclaimer here is Grinnell is a great institution, and I considered a 3-2 program there. So anyway, in 1962, I graduated in agricultural engineering, and Senator Regent Wilbur Mollison personally handed me my diploma on stage. The footnote is Don Peterson, also an ag engineer, is one of the inspirations for my education. Today, the Ag Engineering Department is known as the Department of Agricultural and Biosystems Engineering. Dad was 62. I had always wanted to farm. The opportunity was there, and so I had started a partnership on 1st of March 1962 that lasted 20 years with Dad. So the disclosure here is I never practiced engineering professionally. This paper originated in the Fortnighty Club of Grinnell. Fortnightly is made up of 12 members associated with Grinnell College and 12 community members. I was honored to be selected as a member of Fortnightly 16 years ago by Don Peterson and the membership. Fortunately, Fortnightly members give a paper or a dissertation every other year, which can be in all kinds of subjects. In the off year, you are the host to entertain the club members. It makes for a very interesting meeting and a great questions and discussions after each presentation. The disclaimer here is George Drake, a Fortnightly member, thought this paper worthy of a bucket course and talked the committee into selecting it. So here we are. Oops. But before we begin, my thanks to Jim Arns and Bob Weimer for their technical support. My statement is, I'm not computer illiterate, but I sure am not computer proficient. I've promoted programs on GPS for 20 or more years. I go to the Rotary Club back at the beginning of GPS. I asked the members what GPS stood for, and one member piped up, Great Paint Sale. In the combine and tractor, I can now change fields without dribbling a little string down the road between fields. You farmers know what I'm saying. On the map, between fields, and do the basics. But I think I am still an aggravation to my son-in-law, who is very tech-savvy and sometimes has to clean up my mistakes or forgetfulness between fields when I change fields. This fall, I had to manage Green Star 3, an iPad, and the whole combine, which runs on computers. I got it done, with mostly minor oops. So that's my introduction. And now we'll go to the paper that I presented to the Fortnighty members. Your podium's a little too low, Jim. Or else I'm on too big a throne. Oops. I've been thinking about how to present this topic for 6 months, or even 2 years, since I picked up by chance at the college bookstore a used copy of To Engineer is Human by Henry Petrosky, who was also the author of The Evolution of Useful Things. Having trained as an engineer, I have always had an innate interest in how things work or don't work. Pre-stressed concrete, which is synonymous with our interstates, all the bridges and overpasses. The highly successful space program, except for the Challenger accident. Computers and the myriad applications when they work. Self-driving cars, we are close. My goal tonight, this was presented in the evening, my goal tonight is to review and for you to comment and add your insight into design and engineering successes and failures. What goes into new design ideas? What do we learn from failures? I have always had a strong interest in what goes into projects. The 2x4s, what makes a bridge or a building or a machine stand up and work, be successful. Just ask Susie. We think we make a pretty good team. I design something and make it work. She makes it aesthetically pleasing to the eye and the senses and an enjoyable place to live, our Mayflower home. Together we build a nest and she feathers it and makes it livable. Life is good, whether it is in the hot tub, the big screen TV, or the car wash shower. So let's start with some buildings and projects around the community. Dad was on the building committee for First Baptist Church, the new church building at 5th Avenue and E Street. And just on a historical footnote, there was great discussion as to whether to build a modern architecture, flat-top roof building, such as the Congregational Building in 1950, or a more historical cathedral ceiling building. It was decided to go with the cathedral ceiling, cornerstone 1951. St. John's used the same architecture. There are strong similarities, cornerstone 1953. Someone from the UCC or St. John's can comment. But my engineering footnote is that when buildings commenced and footings were dug, the contractor, Bowers, out of Montezuma, who I believe has a relationship with Coach Bowers, is he the father of Coach Bowers?
Yeah. It was a
Shut the construction site down and came to the building committee with a problem. He stated the footings, what all of the building rests on, were not big enough. Not a big enough footprint. Needs bigger shoes to support the finished building. Oops. The building committee authorized larger footings, and there is not a crack in the building today, 65 years later, due to any settling or shifting of the footings. Let's go upstream to the Episcopal Church, just south of Highway 6. And I believe, and St. Barbara's a member of Fortnighty, can comment on this. And there's others here that are Episcopal, I do believe. If I remember correctly, he presented a paper on moving the Chester Church to the present site. But I grew up on anecdotes of the Baptist Church holding a baptism on that site in the ponds of water accumulated in the wetlands next to the railroad. I'm making a guess that neither the original building nor the new site of Chester Church have basements, avoiding probably a major oops. On the other hand, I drove by the other day and there's windows in the basement of the Chester Church site there, I think. Let's go upstream, but I grew up on anecdotes of the Baptist Church. Okay, across Highway 6 is the Forum, built in the 60s, now an IT center. This is Grinnell College. Once again, my anecdotal stories from Dad are poor soil structure. I would understand the Forum is built on 80-foot pilings driven down to bedrock. Whether the pilings were integral to the original plans or added ad hoc as the construction began, and it was determined that the site wouldn't support the building without positioning it on bedrock. All of that concrete might have just settled into the muck as the trains periodically rumbled by, vibrating it into the jello with each passing. Let's proceed on north to the Barrow Recreation Center. This will be the site of my first structural failure example. And all of you are well aware of the failure. With a big splash, the ventilation distribution system fell into the pool. Of course, the facility was immediately shut down, and luckily, no one was in the pool. The facility was shut down for an extended period of time as the Olympic pool was drained over several days to avoid overloading the municipal water treatment plant. The new ventilation system was rehung, installed, and the pool was refilled over a couple of days. The reason? Someone did not take into account the effects of the chlorine vapors from the pool on the hanging brackets for the ventilation tubes. And other applications, this would have been no problem, business as usual. But in this application, corrosion took over, resulting in a rather major, but luckily non-life-threatening failure. Luck, meaning a major swim meet was not in progress. Another major oops that fortunately did not have a human catastrophe. So now let's go south to what is now Van Wall equipment on Highway 146 south of Grinnell. Van Wall is a John Deere dealer in Grinnell, the successor to Southern Implement. As most of you know, Southern had built a new implement dealership some 15 years ago. The buildings were of steel fabrication, quite commonly used for farm buildings, as well as warehouses for many factories and other spaces needing a large square footage under roof. This past November, December, we had an unusually wet, heavy snowstorm. The snow swept over the north-facing roof and accumulated on the south slope of the roof. There was also a taller structural part next to the lower roof, which probably caused even more snow to accumulate on the lower roof. Regardless, the roof panels sagged, bent the purloins between the main structural I-beams, and pulled in, twisted these relatively massive I-beams that are the backbone, the spine of the building. This caused the failure to run on up to the peak of the building over an upstairs meeting room. Ultimately, portions of the roof completely caved in, giving rise to natural ventilation and lighting of the space. This resulted in the upstairs conference room being closed, offices on the main floor being closed and relocated onto the open showroom floor, and part of the parts department being closed off. Also, the heating and ventilation tubes were destroyed, a rather major inconvenience. Oops. Since then, insurance, the builder, building component supplier, Van Walls, Southerns, and so on have been involved in discussions and assigning proportional blame. And of course, ultimately, to repair the damage and make the space useful again. Although natural lighting has a certain appeal. Look at the library here. Engineering-wise, these buildings are built to two different standards. The first, the heavier duty version, known as commercial, and the second, built to a lower standard, therefore less expensive and lighter duty for agricultural applications, which can be characterized as less demanding and or not needed to be built to a more exacting, higher standard, such as a commercially applied building. No one has acknowledged to me whether this building was built to commercial standards or was chosen to be built more cheaply to an ag application to save money. All engineered structures employ a measure known as the factor of safety. The factor of safety has been referred to as a factor of ignorance. It provides a margin of error that allows for a considerable number of corollaries to Murphy's Law to compound without threatening the success of an engineering endeavor. In this application, Van Wall, the application of safety was obviously exceeded. Oops. My eyebrows raised, Joanne. The factor of safety can be illustrated this way. In the example of this building, assumptions on wind loads, snow loads, things hung from the roof beams, like hoists, are made, and then the beams are designed. Throw in the variability of a bad batch of steel also. Then a factor of safety is applied. A factor of 2 would be to double the estimated loading, and therefore doubling the strength of the beams. I do not know what the factor of safety was used in designing this building, but obviously it was not enough. Other projects involving human safety or having catastrophic results of failure, or the possibilities of exceeding assumptions, can use a higher factor of safety. Roads and bridges are good examples. Railroad locomotives grew larger and heavier. Bridges failed. Interstate highways and roads in general are subjected to more traffic and heavier loads than they were designed for in the 1950s. Look at Interstate 80 after it came through Grinnell. These also illustrate yet another assumption in the calculation of the factor of safety. What is your assumption of the life of the structure and the stress it is subject to during its assumed life? The example for this is in the advertising of the new Buick convertible. The prototype, Cascada, was subjected to speeds of up to 31 miles an hour as the electro-hydraulic mechanism for the roof was cycle tested 15,000 times, the equivalent to operating the top 4 times a day for 10 years. Sounds good to me. And there's math professors in the club. But now you math professors can go to work on the statistics. It might fail after 1 year or after 15 years. But under the engineering assumptions assumed, it did last 10 years, at least. An impractical illustration of this, and I'm not going to hand out paper clips, is the paper clip I am now handing out. Under the usual application of this device, it usually lasts forever. But I want you to abuse it. Open it out flat, straight, and rebend it into its approximate original configuration. Count the number of times you can do this before it breaks. The math guys can have a grand time applying a statistical model to your results. And I have complicated the illustration by handing out 2 sizes of paper clips. A practical application of creating this fracture is when I need a piece of baling wire or even a barbed wire, which takes a little longer, and the side cutters, pliers, or fence tool is not available. How many of you have bent a piece of wire back and forth, stressing it to the breaking point? Now let's extrapolate this idea to a bridge. But first, let's go back in history to the era of building with stone. The top center stone of an arched bridge or cathedral arch is called the keystone. When it is put in place between the arch on each side of the keystone, the downward force of the load is distributed out to each side of the arch. In the case of a bridge, this sideways horizontal force is distributed out to the foundations on either side of the bridge, which are embedded in the soil or more stones or concrete. And it's a pretty stable design if the span is not too long. How many of you have seen the public television program on cathedrals and their arches? That was a fascinating engineering problem in structural design. You saw the pictures of the windows, the arches, the nave, and again, this is the previous Fortnighty paper, that the arches spanned over in the Bill Minner's last presentation. In the older days, the bigger and the taller these arches was thought of in terms of being closer to God and heaven that you could be. Each cathedral tried to outdo the previous one. And today, some still think in terms of higher and closer to God. But then there were engineering failures in these arches because the downward and sideways deflection of these ever bigger and taller arches buckled the columns sideways. Oops. So flying buttresses were incorporated to mitigate this sideways thrust on the columns, brought on by the ever taller columns and wider arches. And the buttresses are those structures to the side to keep them from buckling. In our modern era, we can detect this sideways deflection of these columns with laser measurements that show the minute deflections that create the cracks and that can eventually accelerate into a catastrophic collapse. For me, it was a fascinating engineering problem as they explained these forces and the directions in which these forces were expressed. They also built a model that helped to show exactly how these columns and arches could fail. Even the pinnacles and spires serve a functional purpose on these structures. Besides their beauty and aesthetics, by adding a straight down weight force on the columns, they help to counteract the bulging, the buckling of these columns. The same purpose was brought home to be when Susie and I were building onto our home on the farm. The cement block walls for the basement had been erected. It was fall, and I thought, I can get the backfill pushed in on the trenches before beginning harvest. Good. So I started dozing, pushing the dirt backfill against the walls. Ken Burnham, the carpenter, showed up and said, "Stop, stop," in half a panic. He implored me to wait until he had part or a lot of the structure built atop the basement walls in order to add weight to the basement structure to help those block walls resist buckling against the weight, the pressure of the soil on only one side of the walls that could cause them to buckle inwards. Whoops. Okay, lesson learned. I finished backfilling later, and the walls are good. So pyramids, cathedrals, stone arches may be said to belong to the pre-rational age of structural engineering, seemingly more reliant on physical experiment and construction corrections, aka the flying buttresses, versus a set of blueprints that are hopefully all calculated out with no surprises. Yet these early builders seem to have a certain acumen, knowledge of what they were doing. And sometimes today's structures seem to depend on failure to reach new success. So the term engineer began to evolve in the late 1700s. Certainly, engineers learned from their mistakes and failures, but more science, technology, engineering, and math began to be employed. I want to go to bridges and related technologies next. We could do skyscrapers, dams, tunnels, nuclear plants, ships, computers, space, and other endeavors also. And again, this is an evening, but same way here. But we need to go home in another half an hour. Maybe it's an hour. What is it, Joanne? You got the sign. We touched on the Panama Canal and computers and gas engines in past presentations that I've made. So bridges it is. From the stone arches, we evolved to timber construction, which in some ways were an extension of the principles of a conical pile of sand, like an hourglass, to pyramidal piles of big particles of sand, blocks of stone, instead of the particles, to arches and then cathedrals. In some ways, wooden bridges are essentially a big pile of timber, with some spans gaining some length. I'm thinking railway bridges, whether short ones in the Midwest to longer ones in the far west. The local example is on 2nd Avenue and State Street, where 2nd Avenue passes under the Chicago and Northwestern Railroad. Some fairly massive timbers in that little one-lane wide trestle. But railroad engines became bigger and heavier, and the loads they hauled longer and heavier. The spans needed to be bolstered for the heavier and longer crossings, and the age of steel began to come into play. Wooden spans were subject to deterioration and rot, as well as fire from the steam engine stacks, or even the steel wheels on the steel track. But iron was a new construction material. Cast iron wasn't unlike the stone arches. Compression strength, but not much tensile, not much stretch strength. And even the steel bridges that followed were subject to failure. The engineers learned by error and failures. Engineers learned how repeated stress of steel bridges can cause collapse. The rhythmic beating of the steel trucks on the cars can accumulate. Even though the bending stress can be minute, it adds up. The illustration, watch the rails flex at a rail crossing while you wait for the trains to pass by. Small hairline fractures can accelerate to failure. Also, maintenance can be a factor as steel rusts, corrodes. And then again, you don't have the paper clips, but picture it in your mind. By the way, how are those paper clips holding up? How many times have you bitten them? But they eventually break. Bridges can be built too long and too delicately. Economics, money, and architectural beauty, aesthetics, or practicality can enter into the failure. So how many remember when the walkways, which are bridges, in the Kansas City Hyatt Regency Hotel gave away in 1981? That was news. 114 people were killed and 200 others injured. The original design may have been sufficient, but it was modified so for construction, ease, and practicality. There were two walkways, bridges between upper floors. This to facilitate passage to the opposite side of the atrium. These walkways would be aesthetic in appearance. They'd look pretty, as well as leaving the lower lobby completely open with no obstructing supporting columns for the walkways. Practicality and appearance. To accomplish this, long support rods in the right-hand drawing, long support rods, where we go here, were to suspend the two walkways. Each long rod or bolt was passed through the upper skywalk and on down to the lower one. So all the weight of each skywalk was passed into each of the rods, hanger bolts, was the original design. This would have worked. Well, economics and practicality, ease of construction, and without someone paying attention to the engineering. The first problem was how to make the connection to support the intermediate upper skywalk. The second was the originally designed rods of one piece. The right-hand drawing passes right through. Would have been over 45 feet long, making them very awkward for assembly and installing the skywalks. Somebody had the bright idea of using two shorter rods, the left-hand drawing, two shorter rods instead of the one long awkward one. Drill two holes in the intermediate skywalk for the connection to the lower skywalk and connection to the main upper hanger rod. But oops, this put the weight of both skywalks onto the one intermediate connection versus just the weight of the upper skywalk. Now the stress was doubled in the connection for the ceiling rod to the intermediate skywalk, as both skywalks' weight was passed into the one connection. In the right-hand one, the rod goes clear through and you just had a nut and washer. So all the weight of the upper one is on the same rod on down to the lower one. Over here, just the upper skywalk was on the right-hand side there, and the lower one was down below. So all the weight was transferred into the one connection where the bolt and the nut washer is. And that contributed to it. Then add all the people you can put on both of these skywalks for the view, the aesthetics. Throw in dancing, or rhythmic swaying with the music, and the load is multiplied. With an already unfavorable factor of safety in place, the makings of a disaster are in place. And the doubly overloaded connection gave away, undoubtedly spreading to the adjoining rods of the same kind of assembly, and down came London Bridge. Oops.
How many years after it was built?
That was at, I think, come what the dedication ceremonies for. It was almost immediate.
It was almost a brand new, I mean.
Yes, yes, yes.
Jeez.
They had a big party. And like I say, everybody was standing up there to see what they could see. And then they had music. And you know what music does to us, some of us. So, yes, I think it was almost at the dedication of it. The footnote, whatever. When they were constructing it, they wheeled wheelbarrows full of construction materials, concrete or otherwise, across it. And the workers said, boy, these things got a lot of give to them. So there was, in a way, a warning. But, yeah. Highway bridges. How many of you have driven over a modern, long, suspended bridge, such as the Mackinac Bridge at the Mackinac Straits? Did you take up the offer of a paid driver? Was the weather nice? What was your experience? I have driven over the bridge, and it was interesting, but okay. This leads me, now Joanne, when do you want to break?
As soon as you come to the next.
We'll do this. This leads me to the Tacoma Narrows Bridge. Galloping Gertie. I think KGR referenced that on their. failure on the 1st of November 1940. The bridge was opened to traffic on the 1st of July 1940. It lasted 4 months. The following is an excerpt from Petrosky's book on page 163. Bridge designer Othmar Ammon, I probably didn't pronounce it right, has written, "The Tacoma Narrows Bridge failure has given us invaluable information. It has shown that every new structure which projects into the new fields of magnitude involves new problems for the solution of which neither theory nor practical experience furnish an adequate guide. It is then that we must rely largely on judgment, and if, as a result, errors or failures occur, we must accept them as a price for human progress." From Petrosky himself. The Tacoma Narrows Bridge was one of the most spectacular failures in the history of engineering. This first suspension bridge connecting the Olympic Peninsula with the mainland of Washington State had a narrow, 2-lane center span over a half-mile long. It was an unconventional design in that the depth of the roadway structure was diminished by employing a stiffened girder design rather than the then customary and necessarily deep open truss. Have you got the picture of the Mackinac Bridge too, Jim, or did you just do that one? Okay. Which illustrates that girders to the diagonal braces, like you see on lots of railroad bridges, that was a lot deeper. Well, this was just basically whatever the depth was, but just enough to support the roadway. The Tacoma Narrows Bridge was one of the most spectacular failures in the history of engineering. This first suspension bridge connecting the Olympic Peninsula with the mainland of Washington, 2-lane center span, a half-mile long. It was an unconventional design in that the depth of the roadway structure was diminished by employing a stiffened girder design rather than the customary and necessarily deeper open truss. This innovation gave a slender silhouette whose appearance was dramatic and graceful, but the shallow, narrow span was also very flexible in the wind. The roadway of the Tacoma Narrows Bridge undulated dramatically during construction and continued to behave abnormally for months after it was opened to traffic in 1940. The bridge, which came to be known as Galloping Gertie, drew thrill seekers who wanted to experience the drive-on roller coaster. On the day of the collapse, the bridge's roadway gave fair warning of its final fling, and it was closed to traffic before conditions got too dangerous. The last spectacular motions of the roadway being twisted to destruction were recorded on newsreel film even as the engineers were trying to understand the phenomena of its aerodynamic instability.
We've got about 2 minutes of film on that.
With a scale model. The film of the last minutes of the Tacoma Narrows Bridge is classic, and you can Google films on bridges, but this one. The engineers had not even thought about a wind tunnel test of the model.
You want to show that?
So let's show that, and take a break. Because we get to go home early today.
The Tacoma Narrows Bridge, dedicated in 1940, was the pride of the Northwest. Then the third longest suspension span that became known as Galloping Gertie, as it swayed in the winds sweeping up Puget Sound. 4 months after it was opened, those winds sent the bridge into a rhythmic dance of death. It literally shook itself to pieces. Caught in the middle of the bridge was a Tacoma newspaper man. The bridge twists and sways in its death agony. Since its opening, engineers have studied ways to end its strange vibrations. They claim to be on the threshold of success, but too late. The reporter, Leonard Coatsworth, manages to fight his way to safety, most of the way on his hands and knees. He abandoned his car with a pet dog inside, the only life lost in the disaster. Giant cables are under stupendous strain as the great roadway of the bridge whips about like some fluttering ribbon. These pictures have been acclaimed as some of the greatest ever built. Here it goes. solid side railings were responsible. A twin bridge on the east coast, New York's Whitestone, has side railings that allow the wind to blow through. A footnote to history. The bridge was torn down for scrap and a new one built, but Galloping Gertie will always be remembered.
Let's take your break. You can run that again if you want while there's no sound.
Ladies and gentlemen, we're ready for the second half of Howard's class, and oops.
So, we have new batteries. You're in luck, baby. Galloping Gertie. Okay, there's your deep reinforced or diagonally braced, whatever you want to call it, that I was speaking to, versus the Tacoma Narrows Bridge. And that gives you a lot more stiffness. And like I say, they were testing it in the wind tunnel as it collapsed. They didn't even think to put it in the wind tunnel to see what it would do to it. But anyway. All right. A more recent example of the highway bridge failure is in Minnesota, Minneapolis, on I-35W over the St. Anthony Falls. This failure occurred in the steel trusses of the 8-lane bridge during rush hour traffic. This is working, isn't it? Yeah. During rush hour traffic, the evening of the 1st of August of 2007. 13 people were killed and something like 131 injured. Some of you may recall video of the failure. This is how the National Transportation Safety Board investigation came out. On January 15, 2008, the NTSB announced it had determined that the bridge's design specified steel gusset plates, which tie pieces together, a flat plate, that were undersized and inadequate to support the intended load of the bridge, a load that had increased over time. The National Transportation Safety Board recommended that similar bridge designs be reviewed for this problem. Quotation, although the board's investigation is still ongoing and no determination of probable cause has been reached, the interim findings in the investigation have revealed a safety issue that warrants attention, said NTSB Chairman Mark Rosinger. During the wreckage recovery, investigators discovered that gusset plates at 8 different joint locations in the main center span were fractured. The board, with the assistance of the Federal Highway FHWA, conducted a thorough review of the design of the bridge with an emphasis on the design of the gusset plates. And I don't think it showed a gusset plate in it, it just showed the bridge collapse. That the original design gusset plate led to a serious error in sizing some of the gusset plates in the main truss. On March 17, 2008, the NTSB announced an update on the investigation relating to load capacity and design issues, computer analysis and modeling, digital image analysis, and analysis of the undersized and corroded gusset plates. The investigation revealed that photos from a June 2003 inspection of the bridge showed gusset plate bowing. On November 13th of 2008, the NTSB released the findings of its investigation. The primary cause was the undersized gusset plates at 0.05 inches, 13 millimeters thick. Contributing to that design of construction error was the fact that 2 inches, 51 millimeters, of concrete were added to the road surface over the years, increasing the static load by 20%. And of course, just east of town, we put the blacktop down over Highway 6, so that's what they did there. They put more concrete down for the road surface. Static load by 20%. Also contributing was the extraordinary weight of construction equipment and material resting on the bridge just above its weakest point at the time of the collapse. That load was estimated at 578,000 pounds, 262,000 kilograms, consisting of sand, water, and vehicles for construction to repair The NTSB determined that corrosion was not a significant factor, but that inspectors did not routinely check that safety features were functional. The inspection showed the potential for failure and then was aggravated by overloading. Oops. Kind of fun to, that part of the internet sometimes I enjoy. Sometimes part of it can be left up in the cloud. So, say what? Well, that's what I wondered if it was on. But I changed my hearing aids too, Joanne, so I can't tell. You got control of it back there in the cupboard somewhere, Jack.
We're okay.
On March 17th, there it is, 2008, let's see, we did that part of it. Now, let's go back to Grinnell. Yeah, good. Let's go back to Grinnell and the Mayflower's Water Tower Square. When the excavation for the footings was begun, it was deja vu, the same as First Baptist Church. According to the job superintendent, Kenny, soil boring apparently had been done, but not shared with Story Construction. Oops. The upshot was extra excavation was done, more gravel packed into the cavity, and then footings were poured. So let's hope there are not cracks in that building in 60 years. Pre-stressed concrete beams are used in many, maybe most, of your smaller bridges. Think interstate highway overpasses or underpasses. Like the Bear Creek Bridge north of Grinnell on Highway 146. What, 3 years ago they finished that? In simple terms, pre-stressed means pre-tension, stretching, putting pressure on iron bars, then pouring the concrete beam around these steel bars that are under tension. After the concrete cures, the tension is released. This makes a much stronger beam to be loaded by traffic or other weight in its application. Concrete's got compressive strength. You can pound on concrete pretty hard to make it. But it doesn't take much to break it if it's in a span. While steel got stretched this way, but it will bend this way. So together they make a pretty good beam. After the concrete cures, the tension is released. This makes a much stronger beam to be loaded by traffic or other weight in this application. The engineering principle is iron has tensile strength, while the concrete has a very high compression value. So you reap the benefits of both worlds. Back at Water Tower, the first floor over the basement parking garage, the ceiling of the garage, are pre-stressed concrete beams, slabs, span between the pre-stressed beams on top of the posts rising from the basement floor. After the floor was all laid in place, holes for various pipes and electrical conduits and other passages leading from the upper floors to the basement had to be bored, opened up, and these pre-stressed concrete slabs. Great care was exercised in the precise location of these openings, so none of the pre-stressed iron bars would be cut or compromised, therefore compromising the whole beam. Don't want any oops here. Water tower apartments are all customized. None are cookie cutter copies. All could and were different or according to the desires of the first occupants. Okay, but this increases the cost for material and labor to accomplish this. And somebody forgot to add in the extra time and or cost of this customization. This is again kind of story construction. So, oops. And took a little longer to finish up some apartments, and there was extra cost involved to customize them. And I'm going to skip the story on Dan Agnew. So, hey, we're about right there. Now let's climb the real water tower and stare off into space. This is going to be fairly quick. First up is the Mars lander. I should have Googled this one, but I believe its failure was traced to a very simple error. The darn thing was programmed in English measurements versus metric. Oops. The second one is the Hubble telescope fiasco. And J.R. Paulson's got his own telescope east of town here. But anyway, maybe J.R. can help enlighten us about this oops. The mirrors were not quite right giving a nearsighted view of the far reaches of space. It was mostly corrected by a spacewalk down on a later mission. The other space-related error was the major disaster of the Challenger spacecraft, a really spectacular failure. Engineers had major trepidations about the O-rings functioning properly and the extra cold weather, the coldest launch so far, for the launch of the spacecraft. But they were overruled by mission control. We have never had a failure in all the previous launches, but this launch did fail, and ultimately the loss of the Challenger was traced to the failure of the O-rings and the cold temperatures. A big oops. We can cite a gazillion other oops cases. The Fukushima nuclear reactor was due a great deal to an oops factor. And so, I will leave you with this thought. A robot-driving car is not in the very distant future. You've got Teslas out there now. My new Buick won't let me change lanes or even get too close to the lane markers without complaining. The forward collision control supposedly will not allow me to run into somebody in front of me. Haven't tried it yet, I don't want to. All you need to do is hook up all this technology up to a computer, which is what is being done, and then we better hope all the IT guys haven't made too big an engineering oops. Sideline there, but I've got a niece working on the BOLT, B-O-L-T for GM, and she's a programmer, and they're trying to get all these bugs out for that. About September, I think that'll show up down. That's finished, maybe. But, yep. Haven't made too big an engineering oops. On the other hand, we didn't learn to walk without a few oops onto our padded diapers.
We would welcome any questions from you or comments or experiences of your own. George?
Well, Howard, I may have mentioned this on that night at Fortnighty. I've got one, okay.
Give him the microphone. Yeah.
One story and then one question. Many people, I think, are familiar with the Millennium Bridge in London, which is pretty recent. Oops. It's a footbridge, very elegant footbridge. And when it was opened, the steps of the people walking across began to make that bridge gallop.
Yep.
They had to close it and re-engineer it, and it now is, I've walked across it many a time, and it's very comfortable to walk on now. The question is this, and it relates actually to Grinnell College. When we were renovating Berlin Library, our architect, Van Wees, whose previous library renovation had been the Sawyer Library at Williams College, suggested that we maybe didn't need to air-condition Berlin. That if we just created enough openable windows, all would be well, because that's what they had done in Williamstown, Massachusetts, western Massachusetts. And we fought him hard. And not that I'm a great fan of air conditioning, but for a library with all those books as well as people, we thought in Midwestern climate it would be quite necessary. So the question is, this is pretty low tech. In other words, the experience of the people living in the venue, then with the architects and engineers talking about what should be done. And I suppose, my assumption is that interface is absolutely essential, and that a lot of times the engineering mistakes are because people from outside don't listen to the locals. I'm just interested in any comments you might have.
I think you just commented. Yeah. But the Challenger really was, the engineer said, it's got a problem. But the administrator said, we're going. Yes. This lady was first, I think. She's been trying.
There seem to be lots of recalls on automobiles. What generally causes a recall?
An engineering mistake. Yeah. I was thinking about bringing key ring, but this is the wrong one. See, the latest key rings, they got a switchblade in them. If you got one of the newer cars. You don't get a key anymore. You get this thing that you stick in if the electronics fail. Anyway, the older ones had the key fob, and General Motors had that one recalled. And the slot in it was longer. I took it down to get it fixed. The fix was to make the slot more nearly a circle, because that gave all your keys hanging on that, like we like to do. I got my key on there. Leverage to pull that off into the off position. And if any of you tried to steer a car without the motor running, your power steering is, well, more difficult than you expect. And the whole works. The whole works. But yeah, okay, make the slots smaller. Again, Nisha.
Do you think there'll ever be a really truly driverless car? Do you think there'll ever say, you want to go from point A to point B, you set your GPS, and you go and you don't have to do anything? Will that ever happen?
Not for you and me. I'm not smart enough. Stan Greenwald, which you know the name, but anyway, his grandson, I believe it is, out in California, works for, I believe it's General Motors, don't matter. But his grandson, I think I got the generations right, made the statement to Stan that his son will never learn to drive a car, because he'll just use your keyboard, punch in your destination, it'll deliver to you. So, you and I won't see it. Well, we do, because Tesla's already got a more or less driverless car, except when the sun gets in its eyes and you can't see the semi-truck. But it's coming, it's coming. To give you the background on something like that, Nisha, is my combine is driverless. I still got to turn it at the end.
Oh my gosh, that's right.
But then I could read the Wall Street Journal or listen to the orchestra, listen to the opera as I go across my half-mile row. Because it's automatic header height control for beam to all form. And it follows the rows with both GPS, the great paint sail, and the feelers. So in a 100-acre field, we're good. And we had computer, what's the word I want? But anyway, managed engines before you did in cars, in our tractors.
Yeah, that's right.
So it's coming, it's coming.
Great, wonderful.
And it worked fine until Lance is playing with the computer in it, and not watching where it's going, and he gobbles the tile, the terrace intake, right, to take water in the dark. And I go out the next day, and I say, this thing isn't working right. I get out and look, and I can see where all the damage was. So, but we'll hope that the software programmers are bulletproof. But we make, airplanes are pretty darn safe, but cars you still have a lot of accidents with when you drive with them.
My, our son has a Ford Fusion that parallel parks for them. I mean, yeah. Just,
You push the button, more or less.
yeah.
Yeah. But yeah, we're there in agriculture. We have some folks on the street.
Hey, right here.
I just wanted to say about the driverless cars, there's a house on Broad Street that has a driverless lawnmower.
Yes.
It's fascinating to watch. It knows where to go and it knows where to stop. So that's the future.
Mike's got a driverless vacuum cleaner on the floor. Runs into the dog and the cat, run in and backs off. Yeah, a rum box. Jack, what do you got? Well, we'll find out if it's good engineering. He said it's going to collapse under me. It wasn't defined as a factor of safety for 200 pounds to sit on. George.
I'm wondering if anyone in the room knows the answer to
Take him a
this.
microphone.
I don't think I need it, but
No.
on the question of driverless cars, I have one of these cars, such as you described, that tells me if I cross the lane or, adjust to
Oh, yeah?
cruise control to the speed of the vehicle ahead of me and so on. But if the car gets slushy out,
Yeah.
those camera lenses get covered and everything turns off. So I don't know whether these driverless cars are depending on that, but it's disastrous. You have driverless and you're in slush, it turns off.
Well, you got ABS brakes for years, George. And the ABS brakes take into account the slushiness, so that you don't block up a wheel. It goes one of the others. And that's been there for years. So,
Oh, my.
who's next?
I have a comment on the Hubble
Yeah.
program. Most people don't know that NASA contracted 2 mirrors for the Hubble, one from Eastman Kodak and one from Perkin-Elmer. And to make a long story short, the way that the Perkin-Elmer mirror was evaluated involved a special lens system to make the mirror, which was not spherical, appear spherical so that it could be tested. And there were 2 versions of this compensating mirror lens system. One which was thought to be more accurate than the other. And through a blunder in testing, the mirror was made to the wrong shape. And the problem was the 2 versions of test lens didn't agree with each other. And by significant differences. But the engineers at Perkin-Elmer blindly took the one that they thought was more accurate and didn't trace down the difference between the 2 of them. And so a lot of engineering blunders are just poor judgment on the place of the fact of engineers. They're humans, and they have the information to prevent the blunder, but they don't believe it.
Yeah. That's the Challenger. He's talking about the Hubble telescope and selection of the mirrors, 2 different companies, and that some specifications
But the
were overlooked.
information was there
Yeah.
to tell them that the blunder had happened, but they ignored it.
Yes.
A few years ago, I was watching a dairy farm. Nobody had anything to do with the cows.
Right.
The cow walked into the milker.
I didn't quite hear the last of it, Joanne.
Cow walks into the milker. The computer says how much she should be paid.
Automation in the dairy herd.
Okay. Nobody has anything to do with the cow.
Right.
She walks into this
Right.
equipment.
Yeah.
It measures, it knows from the computer how much that cow should be fed. She is milked, all automatic, nobody touches anything, and she leaves. If she comes in again and thinks she'll get fed again before it's time, it won't do anything.
Right.
But it's all dependent on that cow walking into that equipment.
Wow.
And computer does all the rest.
Yep. As long as the software is good.
The cost of one of those is, each one costs $250,000 at that time.
And do you know that Alliant gives me a rebate to put that equipment in?
Well, they do.
Because it saves energy.
Anyone else?
Hey,
Well, I guess then we can thank Howard for a great class. I want to remind you that this is our last class until January 11th, when Clark Lindgren, who is professor of biology at Grinnell College, will be here. And you will be notified of the registration time, and we look forward to all of that. In the meantime, hope you have a wonderful holiday season. Happy Thanksgiving, Merry Christmas, Happy New Year, Happy Hanukkah. If you have a birthday, happy birthday. And we will see you all again on January 11th. Thank you for coming.